This session is about derivatives of inverse trigonometric functions, as you can read. And we needed to wait for that so that we could use implicit differentiation. So we're going to begin with an introduction to the idea and remembering what inverse trigonometric functions are, in fact, and some of their traits. So a quick review of first the sine function. Here I've got a graph of the sine function. As you can see, y equals the sine of x. And part of it, of course, is a little bolder than the rest of it. The main idea is the normal sine function is a function that doesn't have an inverse function, because what we learned in pre-calculus is that it fails the horizontal line test. A function must be 1-to-1 to have an inverse function, and be 1-to-1 it must pass a horizontal line test, remembering that any horizontal line can cross the graph in at most one point. So this fails the horizontal line test. But now if you focus your attention on the bold red part of this graph, then if that was the only part of the graph, then of course any horizontal line would cross the graph in only one place. And so what I've really done is I've only considered x's between the value negative pi over 2 and positive pi over 2. And if I consider only those x values, then the function does have an inverse. It is 1-to-1. So I redefine the inverse sine function to be only defined between negative pi over 2, the sine function to be defined only between negative pi over 2 and positive pi over 2, and then it does have an inverse. Now remember the trait of inverse functions. The blue graph represents the inverse of the sine function. And remember that trait is that the graphs of the function and its inverse are symmetric about the slanted line y equals x, which is represented by this green line. And you can see then, of course, this blue graph is in fact symmetric to this bold red portion of the graph. The blue represents the inverse sine function, and the bold red represents the restricted sine function. Now remember, the bold red has a restricted domain, that is, only x is between negative pi over 2 and positive pi over 2, but we can still see that its range, that its y values, go from as low as negative 1 up to as high as positive 1. And we're going to, remember, call the inverse sine function by this special notation. Now we can also refer to the inverse sine function with a little bit different notation. Sometimes we call it arc sine. Okay. So the blue graph might be represent what we call the arc sine function. But nevertheless, remember the relationship between a function and its inverse. The domain and ranges are interchanged. So the domain of the inverse sine function is the same as the range of the regular sine function with restricted domain. And of course, the range of the inverse sine function is the same as the restricted domain of the sine function. And you can also see that illustrated maybe if you look at the graph. Let's look at the next slide. Okay, so this is actually the graph of the inverse sine function, and you can see that its domain is from negative 1 to positive 1, and its range is from negative pi over 2 to positive pi over 2, as we just discussed. And if you recall the definition of the inverse sine function, that is, if y is equal to the inverse sine of x, then that means two things. It means that the sine of y must be equal to this x, where y has to fall between negative pi over 2 and pi over 2, as we see on this graph, and x has to be between negative 1 and positive 1, as we see on this graph. So that is the domain and range as we've seen here. So it's very important to recognize the relationship of these functions. That is, if we know this is true, then we know this is true along with these two conditions down here. And what we're going to do in the next part of the introduction is actually calculate what the derivative of the inverse sine function is.